All right, so today we are talking about bonds. And a bond is formed when atoms share or transfer their valence electrons. Remember, those valence electrons are those outermost electrons in order to fill or to obtain a filled outer valence shell. Now remember, we are that electron cloud, we want to be like our nearest noble gas neighbor. So, for example, if I was to look at oxygen, oxygen's electron configuration is 1s2, 2s2, 2p4. And if I were to look at the periodic table, if I look at that S block for hydrogen and helium, that's filled. That's my 1s2. And then I move down to my second row. And if I have to count past those first two columns, those first two S's. And then if I hop over to my P block, oxygen is the 1, 2, 3, fourth one over. Now, if I was to create an oxygen anion, an O2 minus, that means I would have 1s2, 2s2, 2p, and then if I'm going to be like my nearest noble gas neighbor, and if I have two extra electrons, this becomes 2p6, which is equivalent to the electron configuration of neon, right? So this is an atom, an oxygen atom's electron configuration. This is an oxygen ion's electron configuration. And when we share or transfer, so we would be transferring electrons, that's how I got this negative charge to fill out that outer shell. When I transfer electrons to form oppositely charged ions, I create an ionic compound. So to have an ionic compound, I have to have a cation, which is a positive ion, and an anion, which is a negative ion. And they're going to be attracted to each other. Positives and negatives, opposites attract. And they associate in a lattice. So we call this an ionic bond. Now, obviously, forces can greatly vary in lattices. And they're not as strong as covalent. Some are not as strong as covalent bonds. Often, these lattices can be broken apart just by adding water, which means that we're dissolving or hydrating. And that's what's happening down here. We'll talk about that in just a second. So what do we look for? How do we know if we have an ionic bond? Well, the biggest key is to look for a metal, which is my cation, and one or more nonmetals, which is my anion. Some examples is NaCl, sodium chloride, AlCl3, which is aluminum chloride, iron oxide, this is another, so ferric oxide, which is iron oxide. So this would be iron 3 oxide, and the second one is iron 4 oxide. And then here I have aluminum sulfate. So ionic formulas need to show my lowest ratio. What does that mean? So if I was to look down here at this lattice, there are a lot of sodiums. My purples are sodiums. A lot of sodiums, there's a lot of chlorines. So if I looked at this, there's a sodium, 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 sodium. There's a whole lot of them. So if I said that I had Na48 in that whole lattice, and I have Cl, I have 48 chlorines, my lowest ratio of cations to anions, so if I have 48 and 48, I can divide both by 48, right? So my lowest ratio would be 1 to 1. 1 sodium to 1 chlorine. And if I have a 1 to 1 ratio, you don't write the ones. It's implied just by writing the chemical symbol. Now, if I was to look at, and over here I made a little note, We'll be using Lewis dot formulas for atoms a lot in this module. And so a little bit of a review on Lewis dots. Sodium has 1 dot because it has 1 outermost electron. Chlorine has 7 because it has 7 outermost electrons. Now chlorine wants 8. Sodium wants 8. And so what wants to happen here is the sodium wants to give that 1 electron to chlorine. So chlorine just gained an electron and now has a -1 charge. Sodium just gave away that 1 electron, so it now has a +1 charge. Now, when it wants to come into this lattice, it gives a one-time electron transfer. So that results in an ion. Okay, so we do that one-time electron transfer. So I have a Na plus and a Cl minus. And in this lattice, we can see that I have my Na, which is plus, and it's right next to the Cl, which is minus. Opposites attract, right? They're going to be near one another. But they're not they're not merging into one another. It's kind of like two magnets. Two magnets that are attracted to one another are going to be near one another, but they're not molding into one magnet. No, they still are their separate people, separate ions. And we can break this apart, like we said up from above. We can add water and dissolve. So we can separate these. Sometimes it's really difficult to separate them, right? If we have a positive and negative and they're very attracted to one another, there could be a very strong force of attraction. But it can be done. Like we said, we can dissolve, we can take salt and we can add water to it and we can dissolve salt. We can hydrate salt. So if you just have to be able to overcome that interaction. And salt just happens to be exceedingly soluble in water. Here's another example of a compound. Now, if we were to try to figure out what kind of a compound it is, if we were to look, we would look and go, oh, we have magnesiums and we have chlorines. And right here is the key kicker. Magnesium is a metal. So we know this has got to be an ionic compound because of magnesium, which is a metal. It's on the left-hand side of the periodic table. And we also know that this chlorine is a nonmetal. So we know an ionic compound always has a metal and a nonmetal. Now, if we were to try to figure out what its chemical formula is, then we need to figure out that ratio of how many magnesiums to how many chlorines. So I would look at this and I would go, okay, there's 1 magnesium, 2, 3, 4, and I'm going to keep counting for 8, 12, 16, 24. Mg24. And then chlorine are my green dots. So I'm going to count all those green dots. Count them. There should be 48 of them. So to find that least common number between them, so I'm going to divide both sides by 24. I'm going to get 1 and 2. So magnesium chloride's ionic formula represents its lowest ratio. And so my lowest ratio here is MgCl2. Now, if we look at molecular compounds, they are sharing electrons. in a very strong covalent bond. So sometimes we call these covalent compounds. Molecular covalent compounds are kind of used interchangeably, but they are sharing, and it's very strong. So once formed, that strong covalent bond takes on much energy. It takes a lot of energy to break it. We always look for nonmetals together. For example, hydrogen, chlorine, water, peroxide, ammonia, glucose, dopamine, fuel, gasoline, amino acids, proteins, DNA. Again, all non-metals. No metals, very rare if there's a semi-metal in there. Now, looking at H2. So going back to my dot diagrams, I have one electron both, but we know that hydrogen is 1s1. Well, everybody wants to be like the noble gas. It really wants to be 1s2. It wants to be like helium. And helium has 2 electrons. Well, so one hydrogen's electron, another hydrogen's electron, what's going to happen is these guys are going to share. And so these clouds are going to overlap. Sometimes this is also can be shown by a line. So these 2 electrons can be shown as a dash. And then that becomes a very strong bond, that covalent bond. They're sharing electrons, and they continuously share. Unlike that ionic compound, when ions are formed, it's a one-time transfer. So we then have a plus, we have a minus, and they can go about their own ways. But a covalent compound is a continuous sharing of electrons. So now if we were to go back and look, go on in your notes and look at some other examples. Here is that NH3, that ammonia. And again, this, if I were to draw nitrogen, we know nitrogen has 5 outermost electrons. So it wants 8. Well, so these 3 electrons that are single here want one, we want 3 more. So if we take hydrogen, which has 1, hydrogen, which has 1, hydrogen, which has 1, and then we bond, bond, bond. So this ammonia has 3 bonds where it's bonding covalently with hydrogen. Now, here's some other types of representations of compounds. Here's our H2O. So 2 hydrogens, so this would be a hydrogen, this would be a hydrogen, and this would be my oxygen up here. Again, we know that oxygen has 1, 2, 3, 4, 5, 6. So it wants a hydrogen here, which would share, and a hydrogen here, which would share. So then my oxygen has a total of 1, 2, 3, 4, 5, 6, 7, 8. Oxygen's happy because it has 8. Hydrogen's happy because it has 2, like helium, right? And so everybody is happy. This is an interesting structure down here because there's no element symbols. But you're going to see in an exploration, this is a representation of carbons and hydrogens. So how this works is that every intersect or every bend symbolizes a carbon. And then we also assume that all carbons are surrounded by hydrogens. So these are all C's and H's. And let's see here. So then over here to the right, we have another kind of representation. And this is showing us carbon, carbon, carbon. So this would be C3. And then also carbon surrounded by H's. So we'd have 3, 6, 7, 8. This would be propane. And then of course over here we have glucose. Glucose, we can see we've got carbons attached to carbons. There's an oxygen right there. But all of these are non-metals, right? We can see we have no metals in any of these. Nitrogens, hydrogens, oxygens, and carbons are every element on this whole page. So these are all molecular compounds or covalent compounds. Remember, all elements, all of these atoms are sharing electrons. They are all the outermost electrons. So all the valence electrons are being shared.